Is this working? Okay, so in my first lecture, as you'll recall, I gave you a bit of a break from all things p-adic. We were doing purely algebrogeometric things. The party is over. It's time to actually do something p-adic. And today, the goal is to explain how to use p-adic methods to attach a sensible version of de Rham cohomology to algebraic varieties in characteristic P, to smooth mostly affines in characteristic P. So I'll tell you how not to do that in a moment. Then I'll tell you how to do it. But first, let me set some notation. So this notation is perhaps scarier than it needs to be. But it's the level of generality at which I'm going to talk about. So I might as well just say it and then tell you how to specialize if you don't like all this notation. So k, little k is going to be a perfect field. It's going to be a positive characteristic. That means it has a ring of Witt vectors, which means there's a unique, complete, discrete valuation ring where the maximal ideal is just generated by the prime number p, and the residue field is the field k. And capital K is the fraction field of that. So, of course, you're perfectly welcome to think of just taking k to be fp, w to be zp, and capital K to be qp. That will be completely harmless from the point of view of understanding what's going on, because there's already something to do in this case. One slightly more general thing you could do, which is useful for working with varieties over finite fields, is to allow k to be a finite extension of fp, fq, and then take w and k to be the corresponding unramified extensions of zp and qp, to avoid writing things like Witt vectors of fq and frac of Witt vectors of fq. I'll just call those zq and qq. But again, if you prefer, you can just think of those as zp and qp. The one thing you'll lose by thinking of that case is you won't notice the following things, that w, the ring of Witt vectors of k, admits a unique lift of the absolute Frobenius on little k, which is, of course, the identity map on zp, but in general is something more interesting. So that will show up a little later. But aside from that, you're perfectly welcome to think about zp and qp and fp. OK, so the situation I want to work with is that I'm looking at smooth varieties over little k. And my convention today, and in fact, I think all the way through the rest of my talks, is that things in characteristic P will have bars over them, to the point of excess, perhaps. So x bar is spec a bar is smooth, and I'm going to assume it's affine for the time being over little k. So this is optional. So actually, is this pen better than the other one? That's better. Let's try that. Not much better, but a little bit. So I promise I will allow non-affines a little later, but just as in the algebraic de Rham setting, it's conceptually easier, at least for me, to think about affines first, where there's not a lot of sheafy stuff going on. You can just work with modules and rings. So I'll do that. And I'm never going to relax the smoothness hypothesis, even though, again, one can if one is more industrious. So you can define a de Rham complex for this thing. There is a module of Kähler differentials again. And this gives you a de Rham complex. Let's see. Do I want to write these with A's or? Let me write these with A's. So I have A bar, omega 1 A bar over K, omega 2 of A bar over K, and so on. So you can make this de Rham complex and then talk about the de Rham cohomology of A bar or X bar, if you prefer, X bar. But this is much too big to be of any consequence, at least for the point of view of doing things like computing zeta functions, because already H0 is very large. So the H0, so H0 is supposed to have something to do with connected components. Whereas this H0 is quite large. This contains every pth power, because the differential of a pth power is p times f to the p minus 1 times df, and that's 0 in characteristic p. So far from being, say, a copy of the constant field, or some small number of copies of the constant field if your thing is disconnected, this h0 is enormous. So that's a sign that maybe we're doing something wrong. The main problem is that you can't tell the difference between pth powers and constants when you're using differentials in characteristic p. And so the basic way you would try to fix that is to lift to characteristic 0. So this slide is going to stay on for a while as I go through the various refinements of the basic idea. So step 0 in trying to make a sensible de Rham cohomology in characteristic p was to actually do it in characteristic p. That didn't work at all. So step 1 is to lift to characteristic 0. So if I lift x bar to some x over w, which is smooth affine, then I could try looking at the de Rham cohomology of the generic fiber, x over k. Because that's something over a field of characteristic 0. So that has something to do with the original variety, but not a lot. This is in no real sense functorial in x bar. If you have maps between things in characteristic 0, that will very often not lift if you choose your affines badly. And if they do lift, they might lift in many ways. And you don't get a well-defined action on de Rham cohomology. In fact, you don't even get a well-defined space. So for instance, if you take a curve of some genus with some number of punctures, you can lift it to a curve of the same genus with the same number of punctures. And then there's that formula I told you about, which involves the genus and the number of punctures, to tell you how the de Rham cohomology is. But you can lift it in different ways. You could lift it to something which has more punctures, a sort of different genus and more punctures, and you could actually change the answer. So in fact, already the dimension of this thing is not an invariant of x bar. So that's not such a useful thing to do. So I won't do that. I'll try to do something that's a little more functorial. So, well, because I'm only interested in what's going on the special fiber, that suggests maybe I should complete along the special fiber. So that way, I'm in a more Henselian situation. So A bar is the p-adic completion of A. So I'm, instead of working with the affine A, I'm working with its completion along the special fiber as a formal scheme, if you like. So A hat, if you extend scalars to k, you get back an affinoid algebra. And so you can think about this affinoid space and say to yourself, well, is this a good thing to work with? Does the cohomology of this mean something useful? And the answer is, it means something, but it's still not really what you want. You do get a sort of functoriality, which is not obvious, because you can have many maps lifting a given map downstairs. So if you have a map, say, A bar to B bar, let me take a simple example, where this thing is just k bracket x bar, and this thing is also k bracket x bar. You can see about the excess here. I've got bars on my variables. So I have some map like this. So this is defined by x bar goes to some polynomial, p bar. Told you I was going to carry this to excess. So now how do you lift this? So this lifts to, so what is A hat? Well, A hat is what I'll call x, W angle x. So W angle x is the same thing as K angle x, the Tate algebra, except you take coefficients in W instead of in K. So this is just the Tate algebra, but I restrict to series with integral coefficients. And so how do I lift this map to W angle x? Well, I just lift x to x, if you like, and now I just lift the image of x to something that lifts it. So I pick some p of x. This doesn't have to be a polynomial. It could be any series in here. And that extends to a unique map lifting the map I started with. But of course, there are many maps I could have chosen because there are many ways to lift this thing. Lift this thing, p bar, up to p. Because I could always, for instance, add little p, which reduces to 0. And now I've changed the map upstairs without changing it downstairs. So you're not expecting, really, to get any sort of functoriality on the level of the lifted ring. Because you can't see p, so you can't see adding multiples of p. So you don't expect any sort of functoriality on the level of rings. You can hope that it maybe isn't a reasonable hope, but it turns out to actually be justified that on the level of cohomology, everything is OK. That actually is already true here. I'll talk about it again when I get to actual Monsky-Washitzer cohomology. But nonetheless, this is not the right thing to take because the cohomology groups are too big. And so here's the basic reason why they're too big. So look at this example. Look at Wx. So I'm going to take, again, a hat tensor with k is just kx. So I'm looking at this standard one-dimensional Tate algebra, and it corresponds to the closed unit disk as an affinoid space. And I want to know what the de Rham cohomology of this thing is. So what's the de Rham cohomology of the closed? So the de Rham cohomology of the closed unit disk, I claim this is large. H1 of this is actually quite large. Let's see that. In particular, it's not 0, which is maybe what you were hoping. So the reason it's not 0 is, so this is equivalent somehow to saying that the map ddx from k angle x to itself is quite far from being surjective, far from surjective. Somehow differentiation behaves nicely in the p-adic world, but integration does not. So if you take an example like, say I take this thing, p to the n times x to the power p to the n minus 1, p to the n quantity minus 1, that is, and I try to take the derivative of that, or the antiderivative of that. Well, there's some constant which I won't worry about. And then I get, so if this is something, say, runs from n equals, I don't know, 1 to infinity, or could start from 0, that'd be fine too. Then I'd get the sum over here of x to the p to the n. And now we have a bit of a problem, which is k angle bracket x consists of series whose coefficients converge to 0 as n goes to infinity, p-adically, that is. And this series has that property, but this series does not. The coefficients are, infinitely many of them are 1, so they don't converge to 0. If you want to make this even more overt, you could do something like put p to the 2n here, and then the coefficients would actually be, right, so if I took p to the n x, p to the 2n minus 1, then I would get over here p to the minus n, x to the p to the n, and now the coefficients are not only not going to 0, they're actually going to infinity, and you can't see that. So basically, the problem is that when you integrate in p-adic analysis, you lose convergence on the boundary. This is, of course, a distinguishing feature of p-adic analysis, a rather unfortunate distinguishing feature that separates it from classical analysis, where integration improves the situation on the boundary, whereas differentiation makes it worse. So we have to do something. And the way we're going to fix this is to not work with all of, in this case, k angle x. That ring is too big. So p-adic completion was too drastic an operation to have taken. It was too much of a price to pay to get good functoriality. So the discovery that was made by Monsky and Washitzer, sort of playing on ideas of Dwork, is that you can actually get away with a much smaller ring than a hat. There's a notion of what's called a weak completion, which I'll define on the next slide or two. And this notion of weak completion gives you something smaller than the full p-adic completion, it's essentially a sort of Henselization, but in a useful, it's a sort of useful analytic counterpart of Henselization. It gives you enough functoriality to construct a meaningful cohomology theory associated to things in characteristic P, but it's small enough that you don't get this pathology that I showed for a hat. You actually get finite dimensional vector spaces for the Drum cohomology, which was not obvious. It was true in a lot of examples that Monsky and Washitzer showed, but it's actually kind of a hard theorem, which I won't talk about much today, to prove that it's finite dimensional in general. It is functorial, as I said, and perhaps most important for the zeta function application, it satisfies a Lefschetz trace formula for Frobenius. So it's actually, the action of Frobenius on this thing is actually related to numbers of points over finite fields, if you're working with little k as FQ. So now I need to tell you what a weak p-adic completion is. The basic idea geometrically is quite simple. The problem we had before was that I was doing integration on a closed p-adic disk. So I had something defined on a closed p-adic disk, and then I took the antiderivative, some sort of antiderivative with respect to x, and I got something which was only defined on an open disk. Because, as I said, radius of convergence is preserved by integration in p-adic analysis, but the boundary convergence is not. So the way you fix this is to say, well, clearly I shouldn't be looking at functions that are only defined on the closed unit disk. I should look for functions defined on a slightly larger disk. So here's my disk. So I want my functions to be defined on a slightly larger disk. Thank you. Slightly larger disk like so. It could be closed, it could be open, it doesn't matter so much. Because now what I'm going to do is integrate, and I'm going to get that same excess, possibly minus its boundary. So I've lost the boundary, but the boundary in this one-dimensional example is a circle of radius slightly bigger than 1. So this open disk still contains a closed disk of radius bigger than 1. So the property of a series in, say, the variable x being convergent on a closed disk of radius bigger than 1 is stable under integration. And that is the observation that makes this whole theory go. That is basically the Poincare lemma for weak completions, and that's the key to making all this work. So how does that translate into a general definition? So here's the general definition. So A bar is my smooth affine K algebra. So in particular, it's finitely generated over K, so I can pick a surjection out of some polynomial ring. You can lift that by just, if you just take the polynomial ring over W, you can map x1 through xn to any lifts of the images of x1 bar through xn bar, and you get a map like so, which maybe isn't surjective anymore, but at least the image is p-adically dense, because this map was surjective. That's not a problem, because basically the next thing I want to do is complete. So I replace the square brackets with angle brackets. Again, this is my notation for this sort of integral part of the Tate algebra. W angle x1 through xn is just the subring of kx1 through xn consisting of power series with W coefficients. And so this map now is a surjection because this thing had p-adically dense image. So now what I want to do is I want to get something smaller than a hat with which to work. So I'm going to take something smaller than this full ring of power series convergent on the closed unit disk. And here's what I take. This is the so-called Monsky-Washitzer algebra that replaces the Tate algebra for the purposes of computing Monsky-Washitzer cohomology. So elements of this power series ring, W angle x1 through xn, are power series whose coefficients converge to 0 as the multi-index goes to infinity. So this norm, I'm not going to tell you exactly what I mean by this because it doesn't really matter. If you like, you could take it to be the sum of the indices. You could also take it to be the maximum index. Basically, any norm on Rn is fine, because all that matters is that it's equivalent to any other choice, as you'll see in a moment. So these series can have coefficients which converge to 0, but might do so very slowly. I want to accelerate the convergence by imposing an extra condition. Here's the condition. I'm going to take the subring of series for which I can find constants a and b. I guess a has to be positive. I didn't write this on the slide, but otherwise this is not so interesting. So a has to be positive, b doesn't matter. I guess implicitly I'm thinking it's positive, but it doesn't matter. So there have to be some constants a and b such that the valuation, the p-adic valuation of this coefficient should be at least this a times the norm of I minus b. So if you replace the norm by a different but equivalent norm, you might change the constants a and b for any given series, but you don't change the overall condition that these things exist. And again, you're supposed to note that W x1 through xn dagger, well actually let me write k x1 through xn dagger, which is just it's the same thing, but you allow coefficients in k, and since only finitely many of the coefficients, if you impose this condition for a series with coefficients in k, only finitely many of the coefficients will be not integral because they go to 0. So I mean that was already true without the dagger. So k angle x1 through xn dagger is just W x1 through xn dagger tensor with k. And this thing is the rigid analytic functions. So this is the sort of the rigid analytic functions on the closed unit n ball, which extend to some ball of radius strictly bigger than 1. And I don't care what the radius is, because I want to be able to integrate, which might screw up my choice of radius, but it won't disturb the fact that some radius exists. So, right, so this thing admits antiderivatives with respect to each variable, say if you set the constant terms to be 0, or something like this. Okay. So I'm going to make a comment which I'm not going to really follow up on, but it's actually quite interesting. You might think, well, so I built this elaborate theory, or rather Brian did, in the earlier lectures, and we've all been sort of using it throughout, of making these so-called rigid analytic spaces by taking the standard Tate algebras, k x1 through xn, and taking quotients of them, and calling those affinoid spaces, patching them together, and so on. You can actually do the same thing with these, well, rather with these so-called Monsky-Washiter algebras, these so-called, well, or dagger algebras they're sometimes called. So the analog of an affinoid algebra is typically called a dagger algebra because it's somehow conventional to use this dagger for reasons that I don't actually know, but it goes back a long time. I think Dwork introduced this symbol. So you get dagger spaces which are analogous to affinoid spaces. In fact, the points are the same. So this thing has the same max spec as the Tate algebra. The maximal ideals of this thing are the same. You haven't added any points, but you have changed the ring in some essential way. And so you actually can imagine patching spaces together made out of these things to get a so-called dagger space. It will then have a restriction. I don't know if restriction is the right word, but it will have a map that turns it into a rigid space by replacing all the affinoid algebras with dagger algebras with their p-adic completions, which are affinoid algebras. This is, of course, not p-adically complete, right? Because I imposed this strong condition. There is a natural topology for this thing, which you can imagine this thing as a union of affinoid algebras, because convergence on any particular closed ball puts you in some affinoid algebra, and each of those has a topology, and you can take a direct limit topology for those. And that's somehow the right topology to use for this thing. But there is also an affinoid topology, or which is to say just a p-adic topology, in which this thing is dense in the guy without the dagger. So there are multiple topologies that are interesting for this thing. One funny thing that happens when you play with these things is that, so in affinoid spaces, any map between affinoid algebras, any homomorphism between affinoid algebras is automatically continuous for the affinoid topology. For these guys, that's true both for the affinoid topology and for this direct limit topology. So it's actually quite a nice parallel. I don't know when this was first worked out. There is a corresponding theory of formal schemes, which is quite old, which is there's a notion of weak formal schemes due to David Meredith, which originates from about the time of Monsky-Wachtnitzer's work. The corresponding geometric theory, I think, was only really worked out by Elmar Grosseklerner a few years ago, because he needed it for something. It was sort of implicit before that. So these are related to something like formal schemes, in the same way that rigid spaces are related to formal schemes, as in Brian's talk, although I don't know if there's an actual analog of Raynaud's theorem. But probably you can actually deduce it from Raynaud's theorem, but I didn't try. Anyway, so the point is that I've defined a replacement for the ring of power series with coefficients that go to 0, and now I'm going to use that to define the weak completion of A. So all I'm going to do is take it to be the image of this ring Wx1 through xn dagger in A hat under the map. Remember, I had a map that went from W angle x1 through xn to A hat coming from the map, lifting the mapping characteristic P. So A dagger is just the image of the dagger power series. One has to check that this is independent of all choices, but this is not very difficult. You basically, if you have another presentation, you can refine them to a common presentation where you put both sets of generators in, and then you can just check that everything is overconvergent in this sense, even if it was overconvergent before. I didn't write the word overconvergent, but I will. So sort of this dagger is sort of corresponds to overconvergent objects. When you have something that carries a dagger, you might, this word overconvergent is used to describe it. That's not the sheet I wanted to write on. Oh, well, I'll have to cover that up. So, yeah, and the word overconvergent means convergent more than, say, on the closed unit ball. So now that has to go away, I'm afraid. Well, I guess it doesn't have to go away until I use it next. But OK, so now I have, so this is the algebra I want to use instead of A hat. And it has a module of differentials, which is really a module of continuous differentials. But formally, you can just define it the way you might expect. You take generators dx1 through dxn and quotient out by relations. If you have something which is supposed to go, a power series which is supposed to go to 0, then its formal total derivative had better vanish. So if f goes to 0, then you take the formal partial derivatives in each variable and form this total derivative, and you kill that off. And that gives you the module of differentials. Again, it's easy to check that that was actually a well-defined thing. In fact, you can even check that it satisfies a certain universal property. I guess it's universal for derivations into a finitely generated A dagger module. I think that's one way to phrase the universal property. And the way I'm going to define cohomology is I'm going to take this algebra A dagger, form the de Rham complex, tensor up to K, because if you don't tensor up to K, you basically get the same problem with torsion that I had mod P. So you get tons and tons of torsion coming from the cohomology mod P, which was not a really pleasant thing. So I want things to be small, finitely generated, so I'm going to kill torsion, even though there's actually interesting questions about torsion in p-adic cohomology that are not being addressed in these lectures. And in fact, they're even relevant to computational issues, but I'm suppressing that. So for the point of view of the theory, I'm going to take this complex made out of A dagger, extend scalars from W to K, and then take that cohomology as what I'll call the Monsky-Wachtnitzer cohomology of X bar. except I don't really have the right to call it that yet because I'm writing something that looks like it depends only on x bar, and in fact, I've made choices along the way. I chose the lift A, and I chose the presentation. I told you you could eliminate the choice of the presentation, but there's still the choice of A. And so there's sort of a question of well-definedness, and there's a question of functoriality. If I have a map between two things, I haven't told you how to associate a map between the corresponding spaces. So this is not yet a sensible definition, but it is in fact the definition that we'll ultimately use. And I will make the comment here, because I probably won't remember to make it again, that it's sort of a hard theorem to prove that this is finite dimensional unless things lift nicely to characteristic 0, which is the case I'll be interested in later. But it turns out you can actually prove this is finite dimensional always, always. This was shown by Berthelot using methods of crystalline cohomology, by Mebkut using techniques from p-adic differential equations. I can prove something more general nowadays, but I wasn't going to talk about that, so I won't. OK, so there's this issue of functoriality. So I just defined something called the cohomology associated to x bar, but I didn't give you any reason to think that it's actually a functor. Right? De Rham cohomology ought to be a contravariant functor on smooth affine varieties. So if I have a map y bar to x bar, so I have x bar spec a bar, y bar spec b bar, and I have a map from y bar to x bar corresponding to a ring map, which I called f bar, a minus b bar. So there's a theorem. I'm not sure who first proved. I think Vanderput originally proved this. There's a much nicer version of this result due to Alberto Arabia, which says that any map between these smooth affines lifts to a map between these weak completions. However, there are many choices, just as I showed earlier, because you can add p to something, and that often gives you a new map. So there's not a lot of canonicality in this map, but I don't actually care about this map. I care what it does on the level of cohomology. So this induces a map between the corresponding de Rham complexes, and so I get a map, sort of f bar star. Well, this really should have been f. This should have been f bar. This should have been f bar. This should have been f bar star. But so you get a map induced on de Rham cohomology, which I'm calling the Monsky-Wachtitzer cohomology of the special fibers, just by taking this thing and just formally extending the map to differentials, right? The image of, if you have some differential, I can't write on that one, so now I have to write a new one. If you have some differential df, it maps to, f is the wrong letter here. If you have some differential dx, it maps to the differential of fx, maybe f dagger of x. Right, so you just extend by linearity the map f dagger, and you get the map between de Rham complexes. And here's where the magic happens. And this is the amazing discovery of Monsky and Wachtitzer that launched this. Even though the map on algebras was horribly non-canonical, the map on cohomology is completely canonical. In fact, it's even better than that. If you have these two maps like so, you get f1 dagger, f2 dagger, they both lift f bar. You get two maps between de Rham complexes. Let me write the things out. So you have two maps between de Rham complexes. So they both go from omega I a dagger over W tensor with k to b dagger over W tensor with k. These two maps are homotopic, which means, right, you have sort of two complexes like so. You have two maps going like this. Their difference, well, I'm not going to write out right, you have, what it says is that you have maps going, I did this once before. You have maps going from the left side up, I think, like that. And then if you go around this way and go around this way and add the two things together, you get the difference between the maps going across. This is not meant to teach you that. It was merely meant to remind you of that if you've seen it before. The point is that if you have this condition, this implies that the maps induced on cohomology are the same. that's sort of easy exercise if I actually wrote out what it said. So the point is that in a very strong sense, there's a homotopy invariance of this lift. And in fact, it's not just a coincidence that you have this word that comes from algebraic topology where homotopies really come from actually deforming one thing into another. This homotopy actually comes from p-adically deforming this map into this map. You actually construct a one-parameter family of maps where one specialization is F1, one F1 dagger, one specialization is F2 dagger, and you show that all of the guys in that family give you maps in cohomology which are homotopic to each other. So it's really homotopic in the original topological spirit of that word. You're p-adically deforming one thing into another because the two maps are close, because they have the same reduction mod p, and that's where the homotopy at the level of complexes comes from. So yeah, the takeaway here is that you actually get a functorial map on these vector spaces even though they were defined by lifting non-canonically to characteristic 0. And this is the magic. Now, my history is a little bit rough, but my impression is that Grothendieck was a tiny bit surprised by this. But he recovered. He then went on to incorporate these ideas into the theory of crystalline cohomology, which was taken off the ground by Berthelot and Ogus and others. But yeah, this is supposed to be surprising. I mean, if it surprised Grothendieck, it should surprise you too. Yes. Yeah, so you're keeping the same this data, and I guess you're keeping the lift A dagger and the lift B dagger, and then you're changing the map between them. So yeah, I guess I should answer the question that you might be about to ask. Why does that tell you that sort of A dagger itself is sort of a well-defined thing? Is that the substance of the question, or is that? Okay, here's why they don't depend on the choice. Take the identity map from A bar to itself, and take two different A daggers, sort of A dagger 1 and A dagger 2. This statement says there's a canonical lift between them of the isomorphism from A bar to A bar, and likewise going in the other direction. So you can use this not only to get functoriality between different things, but to actually identify two different constructions that are supposed to correspond to the same scheme. So yeah, so you can canonically identify the cohomologies of two different A daggers, two different versions of A dagger for the same A bar, even though there's not a canonical isomorphism of the rings. Yes, but that's what this sentence gives you. It says there always is a map. And there are many such maps. And no matter which one you take, yes. You can choose the lifts first, and then there will be maps. So in particular, if the situation is this one that you ask about, where you have A bar going to A bar, so you might have A dagger 1 and A dagger 2, there are many lifts like this. There are many lifts in the opposite direction, and of course there are many lifts going this way. So this map induces a canonical map on cohomology. This map induces a canonical map on cohomology. Their composition is a map from the cohomology of here to the cohomology of here, which is also invariant under changing the choice of that map. But you can take the literal identity map there, and so. Yeah, so that says that this canonical isomorphism really makes sense. It's the identity when you take exactly the same lift more than once. Yes, Jeremy.
Is the existence of the lift Hensel's lemma, basically?
Basically, it's sort of globalized Hensel's lemma. So if you on the level of the map A to B, it's basically that there's some sort of cohomological obstruction to lifting the map, which vanishes because you're looking at smooth things. And then there might be a global obstruction in general, but there's no global obstruction because you're looking at affine things. So formally, you can lift all the way up, And you can actually algebraize, but you don't need to. You really just, it's enough to get something which works on these dagger things. Yeah, so it's basically because you have no global obstruction because you're affine, and you have no local obstruction because you're smooth. Okay, so yeah, you have a well-defined theory. Now what are you going to do with it? Here's what you do with it. And this is due to Monsky. Now I'm going to specialize in the case where my residue field is finite. So K is my unramified extension of QP. X bar, I have to assume that it's of pure dimension D. And now I take a lift of the Frobenius on A bar, the Q power Frobenius, the one that's FQ linear. And it doesn't matter which one I take, because I always get the same map on cohomology. And I form this alternating sum of traces, minus 1 to the I, trace of, well, I have to flip things around because this Frobenius is the Frobenius on rings, so it's arithmetic, I guess. So things are a little bit backwards. But also because I really should be using, this is something like cohomology without supports. And trace formulas are supposed to be written on cohomology with compact supports. So this is written slightly more cleanly using cohomology with compact supports, but that's a little bit harder to define, so I'm not going to. But this is what Monsky actually proved, is that if you take this alternating sum of trace of Q to the DF, the F dagger inverse, on the Monsky-Washington cohomologies, this actually counts fixed points of the Q power Frobenius, which is to say FQ rational points on the variety. And what this tells you is that you can now compute the zeta function, because you can compute something like this. The zeta function of x bar, which is exponential, this is the easiest way to write it down, t to the, this is some power series in t. This thing, if you apply this repeatedly, replacing q by powers, you get that this thing is an alternating product. Maybe I'll write it this way. P naught's on the bottom. P naught of t, P2 of t, etc. P1 of t, P3 of t, etc. Where pi is the determinant of 1 minus t times this operator, q to the df dagger inverse, acting on the Monsky-Washington cohomology. I think that's right. So you get an explicit formula for the zeta function in terms of the action of Frobenius on cohomology. So for one thing, this tells you that the zeta function is rational if you know that these spaces are finite dimensional, which we do. Of course, we knew that for other reasons, say fundamental cohomology. But it also gives you a really nice way to actually compute, because I claim, and I'm going to back this up with an example that I'll do now. I should have done it earlier. You can actually compute these things. Actually, let me show you the last slides, and then I'll end with the example. Maybe that's better. So you can actually compute using this. And the reason you can compute with this is because this space very often is something you can deal with. And OK, so non-affine varieties, I'm going to say about 10 seconds worth about this slide. For things which are smooth but not necessarily affine, you can sort of checkify the situation, but it's kind of a mess. And I've never seen a completely satisfactory explanation of this that I could sort of present in a small number of minutes. I have a student, Chris Davis, who's sitting in the audience somewhere, trying to fix this. If your thing lifts to a smooth scheme, say you have a smooth proper scheme that lifts, you can actually do this honestly by just using pieces of a cover of the lifted guy, and then you get an honest check complex. But you still have to construct the functoriality locally, because maps don't often lift. If you have, say, two elliptic curves that have a map between them, and you lift, you don't often get a map between the lifts. So functoriality you still have to deal with locally, particularly Frobenius. Frobenius will only lift locally in general, so you have to sort of patch together the information using spectral sequence, if you like. Now here's what makes this really work, is that if you have, let's say there's no z for a minute. Say I just had x proper over w. then there's a natural map from the de Rham cohomology of the generic fiber to the rigid cohomology of X bar, basically by analytification. You take algebraic cocycles on here, you view them as analytic cocycles, and then this rigid, then you could sort of interpret those as belonging to this rigid cohomology. Rigid cohomology being the non-affine version of Monsky-Washitzer cohomology. This is an isomorphism basically by rigid Gaga. We've heard about the Gaga principle several times already. That sort of tells you that this is an isomorphism. And the logarithmic version is if you have a smooth proper pair, so you have a relative normal crossings divisor over W, you again get an isomorphism on complements. This means that this thing, which has Frobenius acting on it, transfers its Frobenius over to here. So the de Rham cohomology of, so this is a very surprising point, and I guess maybe this is really what pricked up Grothendieck's ears. You have the de Rham cohomology of, for instance, an elliptic curve over QP with good reduction. That vector space, which is defined in characteristic 0, in fact, you could, if it started out over Q, you could even define the space over Q and then just tensor up to QP. That space carries a Frobenius action coming from the special fiber, the reduction mod P. So somehow the de Rham cohomology of the generic fiber sees the action of Frobenius on the special fiber in a very geometric way, in a very explicit way, which I'll show in the last small number of minutes. And I'll mention, yeah, so you can use this to compute zeta functions. This gets various people, like cryptographers, interested. It also gets number theorists interested because you can do things like compute the regulator term in the p-adic version of Bert, Swinish, and Dyer, which is the conjecture of Mazel, Tate, and Teitelbaum. So there's a paper of Mazer, Stein, and Tate, which maybe has appeared by now, which gives you a nice way to compute this regulator term using this p-adic canonical height in terms of p-adic cohomology. And this is, if you ask Sage for this regulator, this is what you get. Thanks to several students who are in this room who worked with William last summer. Okay, so in the last minute or two, let me give you just the flavor of how you do this for an elliptic curve. Yeah, I was hoping I had more time to show this, but I'll do this as fast as I can. So here's my elliptic curve, my favorite elliptic curve in Weierstrass form. So my characteristic has to be not, say, 2 or 3, so that this is a good idea. Say P is not 2 or 3. And say I'm just working over, if you like, just over QP. Okay, so I can lift this like so. So this is, I guess, W. So I'm lifting A bar and B bar to A and B. And this is a good lift which satisfies the comparison theorem. And the reason is, so I started out with a genus 1 curve with 1 point missing. Now what I have upstairs is a genus 1 curve with 1 point missing. So the 1 point over ZP is it's a section over ZP, and it's a relative normal crossings divisor. Here's a variation which turns out to be better. So what the theorem says is that the calculation I did to compute the de Rham cohomology of this thing tells me exactly what the Monsky-Washitzer cohomology of this thing is. It has the same generators and the same relations. It's just that here, when you work with a dagger, you just have power series, but you use the same algebraic relations from A. So yeah, so you actually get that the de Rham cohomology of spec A, H1 of that, is the same as H1 Monsky-Washitzer of spec A bar. Okay, so here's the variation. I'm going to have to lose that. So here's a variation. So now what I'm going to do is take out more points. So y bar, z bar minus 1. So I've taken out the points where y bar vanishes. So those are all the Weierstrass points, if you like, which is just to say the 2 torsion points. And now I'm going to lift that using the same sort of equations. Now this is again a good lift because now I've taken out multiple points downstairs, but I've taken out 1 point upstairs corresponding to each point downstairs. I've taken out 1 point upstairs in each residue class that I had to remove downstairs. And that's in general a good idea for curves. Right? If you have 2 points, right? If you imagine spec W is like this, I'm taking out 2 rational points. In order for these two to cross transversely, they have to not intersect. So they have to reduce to different points on the special fiber. So as long as you take out points upstairs, which give you different points downstairs, you win. And that's what I did here. I'm taking out 3 points upstairs, lifting the 3 points I took downstairs. And the reason why to take this A naught instead of A is that you get a really nice definition of a Frobenius lift. So you can lift x goes to x to the p, and then y goes to some expression that it's forced to go to, which I'm copying down from my notes. This times z to the 2p, and then that to the 1/2, and z goes to the reciprocal of this, which you can rewrite. The point is that I made this choice just for convenience. This is forced by the fact that I want the equation, the relation that y squared equals x cubed plus ax plus b has to transform to another relation. F of y squared, f dagger of y squared, has to be the same thing as f dagger of x cubed plus ax plus b. So here I'm assuming w is zp, so that I don't move a and b around. So now you actually can construct a lift on the a dagger that I had before, but it's quite difficult. You could sit down and try to do it, but you only know it's there because the theorem tells you it's there. Whereas if you allow yourself to divide by y, basically I'm dividing by y over here. Or in other words, I'm taking out the points where the map down to P1 ramifies. So I'm lifting, I have an obvious lift of Frobenius on P1, which x goes to x to the p, and I'm lifting that up to my elliptic curve. This gives you a very easy to write down Frobenius map. And this is, in fact, what I used in my paper from 2001 to compute zeta functions of elliptic and hyperelliptic curves. And this works incredibly well. As I said, this particular genus 1 case is built into Sage, mostly by, let's see, so the people who did this are sitting in this room somewhere. I think Jen Balakrishnan, David Rowe, Liang Shao, and David Harvey. If there's anybody else, I apologize, but that's the names I knew about. And it works really extremely well. I have to clean the air filter, apparently. That's telling me it's time to stop, I think. So I think I got through everything I wanted to say. Yeah. The comparison theorem? Yeah. So what I'll do next time, just to preview in finishing, is this was a really useful technique for computing the Frobenius action in p-adic cohomology and consequently zeta functions for a single variety. But one of the powerful things about p-adic cohomology is that it actually lets you talk about cohomology not just for a single variety, but in families. So next time, I'll explain how to look at de Rham cohomology and p-adic cohomology in families and actually take advantage of an interesting extra structure you get called the Gauss-Monning connection to give a new technique for computing zeta functions. But I'll stop now for here. Yeah, Brian.
So you say that this is very computable.
Yes.
So you describe the map, but you actually have to calculate this homology.
Okay. So for A, for the version without taking out the extra points, I already told you how to do this yesterday. For the map for A0, so again, A0 and A0 dagger have the same cohomology. So I haven't actually told you how to do that, but I can tell you in about one sentence what the basic idea is. If you have so when you write down this Frobenius, maybe it'll be 2 sentences. Well, first, one sentence will be about Frobenius. When you apply Frobenius, of course, you don't actually compute an infinite series. You truncate, and you have some finite, very long series that is your approximation. And so you will formally apply that to your 2 basis vectors. And now here's the sentence about rewriting in cohomology. You have some large power of y in the denominator when you do this, because you're dividing by y here. You have a z here. So you have some large y in the denominator. And it's quite easy to write down a relation that relates something divided by y to the, say, 2m plus 1 to something else divided by y to the 2m minus 1. So for instance, if I took x cubed plus ax plus b and put that over y to the 2m plus 1, then I could cancel the top of the y squared. But there is another relation that actually puts the derivative of x cubed, that puts 3x squared plus a on top, and puts y to the 2s plus 1 on the bottom, and rewrites that in terms of y to the 2s minus 1. And since you can write everything in terms of a polynomial and its derivative, if they have no common roots, you can use that to clear poles. So you sort of successively clear the poles until you don't have anything except things like dx over y and x dx over y. So that's how it works.